only Lawrence Krauss. He's the director of Origins Project, Arizona State University, foundation professor at ASU's School of Earth and Space Exploration. His talk is called Rivers in the Dark, exploring hidden wonders in the sky and things that go bump in the night. As a kid, there was a ravine next to his house. They used to build little tents and they would hide there. His favorite chocolate is a Kit Kat bar. He prefers a shower. I asked what he would name his boat, and I thought it'd be something fun like, Gone Fission. Terrible. But he said boat, which I think is actually way better. And the question he would ask, which is a legit one, are the laws of physics unique? Please welcome Lawrence Krauss.
Thank you. It's good to be here. It's always good to be introduced by George. I never know what will happen. So let's see. Well, yeah, we should get the slide back up there, not me. This is a quote you've all heard from William Blake, and I've been thinking a lot about it lately, because I get asked to give a lot of talks lately, and I just was, in fact, with David, he was here on a trip to David Thiessen on a trip to Amazon with Richard Dawkins, and I prepared a talk, which I've adapted for tonight, about the Milky Way. But the point is that what is amazing about science, and I guess this is what I want to begin with, is this, and there's my Origins project, is this notion here that I put, I think, in the abstract that they asked me. But the wonder of science, as opposed to religion, is that we can follow nature beyond the evidence of our senses in an open-minded fashion, where preconceptions disappear. And anywhere you start, whether it's a grain of sand, a speck in the night sky, if you follow the evidence nature provides, you find amazing things. So I picked the galaxy today, but I made a decision that, and I know I'm speaking, I think I've just agreed to speak at SciCon again in October and these things. And what I'm going to do is something I used to do when I was a kid, when I worked at a science museum. But I'm going to, next time, and I'd be happy to do it now, but I already have these slides set up. But I think what I'm going to ask the audience to do is pick 3 things they like that they see in the natural world. And then I'll just do a lecture following them as far as we can to the forefront of modern science, because it'll be more interesting for me, because then I don't know where I'm going, and maybe more interesting for people. But I picked the galaxy now. So if you're coming to SciCon, you can think of something absurd to make it more difficult for me to do next time, and it'll keep me alert. But in any case, how many of you, damn lights are really, how many people you are from LA here, live in LA? You don't have to applaud, it's not worth applauding. But, okay, for those of you, I want to show you stars. Okay. Just watch this for a while, I'm going to take a drink. Sorry for the New Age music. These are real shots where people actually live. Okay, I've heard enough. It goes on for another couple of minutes, but this is a particularly pretty shot of the Milky Way galaxy. And when I was thinking about talking about the galaxy, I also thought, since I was with Richard, and Richard does this, so I'm going to do it for a little bit. He reads from his own books, and but he does it in an English accent. I can't do that. But it reminded me of the fact that which is true whether you live in Los Angeles or any city, of something I wrote a long time ago in a book I wrote called Atom. And so I'll read it here for a second. In the great cities of the world, we've detached ourselves from night. If you're a city dweller who doesn't believe this, travel at least 100 miles to the countryside, go to the highest hill and stare at the sky. It's not the same sky at all that you see here in this city. In the city, the stars overhead can glitter like lights on a distant rooftop, and the sky begins beyond the horizon. On a clear night in the mountains, you become part of the sky. The stars reach out and touch you, and suddenly you feel the embrace of a galaxy. That's what you can see here. And when we were traveling in the Amazon in the dark, I thought it would be a particularly appropriate time to talk about that, because in fact, I remembered something I'd written about South America, which is, and the rest of the world. Even today, the Mercy peoples of Ethiopia associate the annual flooding of the Omo River with the heliacal setting of the stars in the famous Southern Cross. And then there's villagers in the Andes today take this connection to the logical extreme. The Milky Way, and this is particularly worthwhile seeing here, because it's a river actually in Peru, right where we were in the Andes. The Milky Way is viewed as a celestial extension of the Vilcanota River, which is a river actually that goes up to Machu Picchu, where we were also visiting. Circulating waters from the heaven to the earth. So for not just for, this was true for the Incas. They had the same view, that their river would be connected to the Milky Way galaxy. And you can see it's not such a bad notion when you look and you really see what the night sky looked like to those people, not today. But that's the sort of religious view. That's the Milky Way as seen as for the first people who tried to think about how the world worked. And what I want to do now is take that simple, beautiful view that you get from Earth and take it as far as science has taken it in a variety of ways and show you some things that I think are interesting about the galaxy. So that's what I'm going to do in the next couple of hours. Okay, this is the galaxy, and as I often asked at this point to see who's have hangovers and stuff from whatever you were doing last night, this is not our galaxy. Why? Okay, we're in it. Okay, good. Most of them. Good. Okay. Well, you're in it. Yeah, most of us are in it. Not the Republican Party, but most of us. But okay. So, but the reason I show you this is the Andromeda Galaxy, and we'll maybe take a look at it later. It's the nearest large galaxy to our own, but it's very similar to our own. It's a spiral galaxy, and the thing about our galaxy is that we can't see most of it. If you live in the southern hemisphere, like my wife, who's in the back, used to when she lived in Australia, you can see much more of our galaxy. It's much prettier night sky in the southern hemisphere because most of our galaxy is visible. But it's still, most of it is invisible because of dust. So if we want to see galaxies, we look out and we see this one. It's about 2 million light years away, and it is almost a clone of the Milky Way galaxy. And it is also, by the way, just out of interest, heading right towards us at about approximately 100 kilometers per second, about 60 miles per second. It's heading towards us. So if you work it out, in about 5 billion years, it will collide with the Milky Way galaxy. And that won't be terrifying. In fact, the night sky won't change much at all. This will get bigger and it'll get more beautiful in the night sky. It'll look that big before it gets to us. But the galaxy is mostly empty space, so actually when the two galaxies collide, almost nothing will hit anything else. It'll just merge together and form a galaxy that's no longer a spiral galaxy. It'll be a big round or elliptical galaxy. But the night sky, for any beings that are on that, will still look more or less the same. There'll be a lot of stars out there. And it'll just be a very different night sky. But the fact that we haven't been able to see our own galaxy until very recently is kind of interesting, because how do we know it was a spiral galaxy? We used to say it was. And so there's another video I thought I'd show, which I found, and it's interesting. It's not that old, but it's still out of date, so I want to show it. But nevertheless, it gives you a sense of the scale of our galaxy. So it starts with somewhere, maybe Chicago, I don't know, where I just was last night. And then it's and then there's the Earth and the Moon. But it's going to take you out to see the galaxy, to give a sense of how big it is. So the Earth has now disappeared into the distance, almost. And you're beginning to see Mars and the Sun. traveling ever faster here, of course, there's asteroid belt. Oh, see, you already know. And then Jupiter. So we're still in our solar system. We haven't even left the safety of the cocoon that our sun provides, which is a large magnetic field and solar wind that really protects us from cosmic rays coming from the rest of the galaxy. The interesting thing is that humans have launched their Saturn, have already launched devices that can go out beyond here. When this film was made, that we hadn't actually launched Voyager and other satellite like New Horizon, which now sees Pluto, hadn't yet visited the planet. So these were images from telescopes and what you imagine Pluto, Uranus, and Neptune looked like. But we're still within, even after traveling all this time, we're still within the cocoon of our galaxy. And many of the outer planets have rings, just like Saturn. Saturn's rings are not unique in any way. In fact, they're quite common. And James Clerk Maxwell, by the way, was the first one to explain that in a high school thesis he did. So we're now leaving the solar system. And we're beginning to look back. I think that's the sun back there. As you can see it, the sun is still the brightest object in the sky. We haven't even gotten yet anywhere else. But already at this point, it's moving so fast that you're beginning to see what this artist at the time imagined the outskirts of our galaxy, or the stars in our galaxy would look like if you were moving away from the disk of our galaxy. It's not a very accurate picture, but it's okay. But you can see the fact that our galaxy is, of course, not static. It rotates. We'll maybe get there. This is far faster rotation than real time because the galaxy rotates and orbits, the outer stars orbit around the inside of the galaxy once every 200 million years. So our sun, which is about 5 billion years old, has orbited around the galaxy about 50 times. Which is interesting because it means that the stars we now see, of course, were at another time on the other edge of the galaxy. What we imagine is the fixed night sky, which of course all early civilizations did, and the Christian Church did, because they said the stars were inviolate, that the heavens were created and static are not static at all. They move. And the fact that the sun has gone around the galaxy 50 times is quite significant when we get to things that I'll talk about later. So that was the picture of the galaxy these people had, because we've never had a picture of our own spiral galaxy. And you're all supposed to be skeptics, so you should be skeptical if we're living here and we see a bunch of stars. If you look out at the night sky, you see stars in all directions. So how do we know that we're in a spiral galaxy? Well, it turned out in 1992 we were finally able to get a picture of our galaxy, which hopefully I'll get. Hopefully. There we go. This is the very first picture of our galaxy as seen from the Earth. And this is the first picture because most of our galaxy is obscured by dust. So you can't see it in visible light from the surface of the Earth. But the Cosmic Microwave Backgrounder Explorer satellite, which was meant to look at microwave radiation from the Big Bang, also looked at infrared radiation and microwaves which could not propagate through the surface of the Earth, and actually looked out at the galaxy from where we are. And you see, we do live in a spiral galaxy. This is our galaxy. We live in the edge, and we're looking inward. It's an amazing picture. It's one of a number of pictures. This didn't win the Nobel Prize, but several other pictures the satellite took did win the Nobel Prize. So we do know we live in a spiral galaxy, which is kind of interesting. Why do we live in a spiral galaxy? That was a big mystery. And it was sort of solved by classical dynamics. You can show in physics that if you take a bunch of gas and have it collapse, there's an instability to forming a disk. Great, so there you go. The problem is it's unstable. And the galaxy is 12 billion years old, except in Texas, maybe. But in the rest of the civilized world, it's 12 billion years old. And so the galaxy should not be a disk after more than about 500, 600 million years. It's unstable. And this was a problem. It's a problem that got solved by an accidental discovery of other things that I want to talk about. This is, by the way, they produced a nicer, prettier image of that by embedding it in the stars you can see. So that's the image that the Kobe proofs that you can then get posters of. But that's our galaxy. And you live in the first generation of humanity that's ever had a picture of a galaxy. So it's already a neat time to be alive. But the modern era began with several other accidental discoveries. But let me point out that we live in a time that's particularly interesting, not just because it's the first time you can see our galaxy, but it's the first time we've known that our galaxy isn't everything, isn't the universe. My mother was born in 1921. She's still alive. And when she was born, and when she was, in fact, probably first started school, the conventional wisdom of scientists and everything else was that our galaxy was it. The Milky Way was the universe. There was one galaxy surrounded by eternal, empty, static space. That was a conventional scientific wisdom less than a single human lifetime ago. This is Edwin Hubble, and some of you have heard me tell this joke, but I'll tell it again anyway in case there are any lawyers in the audience. No one wants to admit they're a lawyer. Okay, well anyway, this is Edwin Hubble, who began life as a lawyer and then became an astronomer, so there's hope for lawyers. And I'm not going to talk about the big discovery that he made that the universe is expanding. I've talked about that before, probably many people in this group. But the important thing that he also did, this is the Mount Wilson telescope. In 1925, there was the first large telescope. He was able to look out and for the first time see that these fuzzy things called nebulae, which is Latin for fuzzy thing, literally, were not star systems in our galaxy. He was the first one to discover there were other galaxies. 1925. Until that point, we didn't know of anything but our galaxy, one galaxy. Now we know in the observable universe there are 100 billion galaxies in a single human lifetime. Think how that's changed our picture of the universe. It's hard to imagine anything changing more than that. Our picture of the universe has changed tremendously in the lifetime of all of you, even the youngest people in the audience. Now, to study our galaxy and other galaxies, we use this is from Phoenix, near where I work. These are two cowboys on the plane, and one is looking at the other and says, I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes due to the Doppler effect. And so you all know that when a train whistle comes towards you, it sounds higher. When it goes away, it sounds lower. And the same is true for different reasons for light. And we can use that to study those other galaxies, which we can see so much easier. We live at the edge of our galaxy. We can't look in, except with microwaves and infrared, because there's dust. But because we're at the edge, we can look up and see all those other galaxies, like the Andromeda Galaxy. And when we look at them, we use the fact that when an object is moving, so a star emits light of a certain frequency. When it's moving away from it, as many of you know, the light gets stretched, just like sound waves do, but for a very different reason. And we call it redshifted, because red light is the longest wavelength visible light. And then when it's moving towards us, we look at blue light. So if we're looking at a galaxy and it happens to be oriented correctly to us by chance, we can actually see its motion by looking at the blue shifted light in the direction the object's moving towards us, that part of the galaxy is moving towards us, and the red shifts the light away, and we can actually measure its rotation. This will come back and be interesting. So I hope. It'll be interesting to me, so I don't really care about the rest of you. Now, we can use this to weigh the universe, but particularly we can weigh our galaxy. And that was a serendipitous discovery that actually solved this problem about why our galaxy exists. This is, I took this picture on the Isle of Ven myself. It's an island off Sweden, Swedish island. It used to be a Danish island, but Sweden is like the sort of US of the Scandinavia. It's imperialist. It sort of takes over everything. And so it took over this island. This is a guy who doesn't have the tip of his nose, so some of you know who he is. Tycho Brahe. He was almost the last person to see a star explode in our galaxy, and at that time it was a big deal because the emperor gave him an island because of that discovery, and he built an observatory, and he was a real creepy feudal lord, a really interesting fellow. He had kept a pet reindeer and a pet dwarf, and on a chain, and he was a very weird man. He built his observatory, which I visited. It's usually closed, but on the island. And the interesting thing is he looked up and for 20 years, with noble tradition, he worked on his back, No one laughed at that joke, but I'm thinking. Anyway, he looked up and he just recorded the positions of the planets in the sky. And the amazing thing is, he did it 10 times better than anyone had ever done it before in all of history, which is amazing. Anytime you can prove things by a factor of 10 is just remarkable. And I think since it's late in the afternoon, I want to make this interactive, so I'll ask you a question. I went to the observatory. It's actually underground. It's built below ground. Why? If anyone gets it, I'll be amazed, but I just wondered. Thought David might know. What?
Light pollution.
Was that light pollution? No, this was the days before light pollution. This is when you could, this is when you could look up and see the sky at night.
The ground didn't move.
Close. Wind, but wind is very good. Wind is the key point, really. It keeps you away from the wind. But the point is, this was before the invention of the telescope. The telescope hadn't been invented. So the way he measured the positions of planets in the sky was with sextants and things like that. So what you wanted to do was get below ground so they wouldn't move. So that's why his thing is like in a crater. It's really kind of interesting to see. The telescope hadn't yet been invented. So he discovered something interesting. Well, actually, he just didn't discover anything except he took a lot of data, which is the basis of science. Most of science is data taking. Then he got kicked off the island because he was a creepy feudal lord, and a new emperor came in, and he moved to Prague. It was a nicer city anyway. And then he got a hapless assistant named Johannes Kepler, who was the exact opposite of him. And I could go into long stories about Kepler, but I won't, because I'm probably already talking too long. But he did what we all do to our assistants. He gave them the data and said, figure it out. And Kepler spent 20 years trying to figure out, and amazingly discovered laws of the motion of the planets that allowed Isaac Newton to become famous. So what Kepler discovered, truly, he would never have been if it hadn't been for Kepler. So this is what Kepler discovered, a regularity. This is the velocity of planets around the sun. And I took this data from a high school or university introductory astronomy textbook. And I would have fudged the data if I had to, but I didn't have to. It's fit perfectly by a curve, and the curve it's fit by, and this is what Kepler discovered. All of Kepler's laws can be codified in a single equation. The square of the velocity of planets around the sun falls off as 1 over the distance from the sun. Now that may not sound profound or useful, but it is, because what happened is that Newton said, aha, if I develop a theory of gravity, if I say gravity looks like you all learned in high school, goes like 1 over r squared, I can prove that planets will go around the sun with a velocity that depends on 1 over the square, 1 over r. So velocity squared goes as 1 over r, velocity goes as 1 over the square root of r. But more importantly, I can find the constant of proportionality. It's the strength of gravity times the mass of the sun. And this was, first of all, it explained the motion of the planets, and he used the same thing to look at the motion of the Earth and an apple on the Earth, and to show that there was a single law of gravity that applied to apples falling on the Earth, the moon going around the Earth going around the sun, and all the planets going around the sun. And that the fact that the whole cosmos could be understood in that way was profoundly important. We just saw, in fact, the burning of witches in an earlier picture today. And it's been said, and I don't know if some historians have argued, that Newton's development of the universal law of gravity was partly responsible for the ending of the burning of witches, because it showed that, as was pointed out, that physical effects have physical causes, that you don't need to blame supernatural things for what happens, and you don't need to blame witches for bad things happening. So the fact that the whole cosmos could be comprehended by a single law may have indeed been one of the key factors in making the world a better place. Okay, it's interesting. Okay, but when you see this, this is interesting, because when I used to, many years ago, when I was when I got my PhD and I was a postdoc at Harvard, I was writing scientific papers, and I learned something very important, which is, if you write a scientific paper, the most important thing you can do is come up with a sexy title. It's true for books, but it's true for scientific papers, because there's so many papers written every day that if you want to get people to read it, you got to come up with a title that'll get people to read it. Now, this is relevant because, see, Newton didn't know the strength of gravity, so he couldn't determine the mass of the sun. He couldn't determine the mass of the Earth either, because you could use this for the moon, whose velocity we know and the distance from the moon, so you could measure the mass of the Earth. The first person to measure the strength of gravity was a guy named Cavendish, 100 years after Newton. And it's an interesting way, but I won't go into it again here. But Cavendish, when I looked at his paper, it wasn't called On Measuring the Strength of Gravity. It was called Weighing the Earth. Because he realized if he was the first person to measure the strength of gravity, he was the first person to know the mass of the Earth. And he was. But the neat thing is, we can use it to weigh the mass of the sun, because we have these great measurements of the planets around the sun. So here's the law of prediction of Newton. And if you put this curve up, the sun would be more massive, and you push it down, it's less massive. Here's his prediction. And so by fitting the data, we know the mass of the sun. That's how we know the mass of the sun. We weigh the sun by measuring the speed of the planets around the sun. And the fit is so good that in principle, you could measure the mass of the sun this way to 1 part in a million. But we can't. Why? Yeah, I'm going to make it really tough. No, the elliptical, they're not quite circular, but that's not the reason. And you don't get a prize if you, like George did, if you answer these questions. But it may surprise you, but the reason we can't is that gravity is, of course, the weakest force in nature. And it's the worst measured force in nature because it's so weak. So we don't know the strength of gravity to 1 part in a million. And therefore, our limits on the ability to measure the sun's mass and all other masses is due to the fact that we only know the accuracy, the strength of gravity, to about 1 part in 100,000, even after all these years, because gravity is so weak. So we're limited by our understanding of the fundamental forces, but still 1 part in 100,000 is not bad for the sun. So we do this, and we do the next thing that science is always, that's really important about science, and that is, if it works, it's like Hollywood. If it works, copy it. And keep copying it. Halloween 23, whatever happens, Spider-Man 18. Or just do the same movie over again, which it seems to be the new thing, you know. Okay, so this again is the Andromeda Galaxy, but if this were our galaxy, we'd be here in the edge. And I told you that the sun goes around the galaxy once every 200 million years. The sun is moving, as you are moving, and we are moving at this instant, at 220 kilometers per second, probably about 160 miles per second around the galaxy. We're barreling. We don't notice it because we're moving at a uniform speed. But so the sun is moving. So the point is, look, we know the distance from the sun from the center of the galaxy. It's about 30,000 light years. We know its speed around the galaxy, and we're at the edge of the galaxy, so we can weigh the whole galaxy that way. And we do it. There's the galaxy we're going around. So we do it, boom, here's one number, the sun, about 220 kilometers per second. A known distance, this is using something called parsecs, but it doesn't really matter. That single number allows us to measure the mass of the galaxy. And we do it, we make that measurement, and we get it, we jump up and down with joy, as you are doing now, I can see. Because we get that the mass of the galaxy is 100 million stars. 100 billion stars, forgive me. 100 billion stars. And the reason we're excited about that is if you count the number of stars in the galaxy, it's roughly 100 billion. So it works, which is always nice. But we can do better. Let's look at objects that are further away from the center of the galaxy than our sun is, and try and do what we did for our sun, and do a better job and measure the mass of the galaxy more accurately. And this is what we started to do. And the first person to really start to do this was a wonderful woman named Vera Rubin, who was an astronomer who was, she had wanted to go to Princeton to do her PhD, but Princeton didn't allow women in the 1960s. So she did it at night school in Washington, and was a wonderful astronomer and a wonderful human. I knew her well. And she started to measure things, and look what happens. If you got this result in an undergraduate physics laboratory, we'd fail you, because it's supposed to follow this curve. And you look at objects like globular clusters or the Large Magellanic Clouds, satellite galaxies, out to 10 times the distance from the center of the galaxy that we are, and instead of the galaxy ends where we are. We're at the edge. Instead of falling off like it's supposed to, according to the law of gravity, it remains constant. And she was the first one, along with other collaborators in Australia and other places, to show something really weird. The velocity of rotation of our galaxy remains constant, even as you go out to 10 times the distance from the center of the galaxy. Now, there's two possible explanations. It's either the data is wrong, and it's astrophysics, so that's likely, but it isn't. Or gravity doesn't work anymore. Or, since the velocity of objects goes as the strength of gravity times the mass enclosed in that region over r, if it remains constant, that means the mass, as you go out to ever larger regions, must increase as radius, so that mass over radius is a constant. So that means out to 10 times the distance from the center of the galaxy, there must be 10 times more mass out there than there is here. But we're at the edge of the galaxy. So 90% of the mass of our galaxy must not shine. And physicists, with their linguistic perspicacity, call that dark matter. Now, when you see something like this that is so anomalous, as a skeptic, you should again be skeptical. This is one measurement which seems to be ridiculous. It says that most of the mass of our galaxy doesn't reside in stars or anything, hot gas or anything. So happily, this isn't medicine. So we can look at many samples and do real science. And we look at another galaxy at its rotation curve, and it's constant. We look at every spiral galaxy we can see, and here are some spiral galaxies whose we can measure the density of stars in those galaxies. We can determine, therefore, if the mass of the galaxy is only in the stars, what the rotation curve of those galaxies should look like, and it doesn't fall off. It's constant. Every single galaxy we see is a constant flat rotation curve. That's what tells us that all galaxies must be dominated by dark matter. And in fact, a big sphere of dark matter. 90% of the mass of the universe is invisible. But that solves the problem, it turns out. Not only is it true, but it solved that long-standing problem. It turns out if you embed a disk of gas in a spherical amount of matter, you have a big sphere of matter, and it remains spherical, then that disk will be stable. So the reason we have a spiral galaxy is precisely because we're embedded in a halo of dark matter. Now, why doesn't the dark matter collapse to form a disk like the rest of the stuff? It won't do that if it can't emit light, because the way you collapse is by emitting energy. But if it doesn't emit light, then it doesn't interact with electromagnetic radiation. And that, we think, means it's made of new types of elementary particles. And what we think the dark matter that dominates the galaxy is a new type of elementary particle. And we are trying to find it. One of the reasons I got into cosmology as a particle physicist is that, well, first of all, I want to know how the universe would end, which seemed like a good idea at the time. But also because by looking at trying to find this dark matter, we might learn about the fundamental structure of the universe. Because if the dark matter is not made of planets or stars, if it's made of new type of elementary particle, it's not just out there. It's going through this room. It's going right through your bodies right now as you nod off during this lecture. And that means we can build experiments underground to look for it. And we're doing that. That's what we've been doing for the last 30 years. We haven't found it yet. But if we do, we'll discover the nature of the dominant stuff in the universe. Now, it turns out not only does it dominate our galaxy, not only does it allow the shape of the galaxy to be what it is, but it allows the galaxy to exist. If dark matter hadn't been there, we can show in the entire history of the universe there would not have been enough time for normal matter to collapse to form stars. And we know that by building artificial universes on a computer. So here you can you'll see this blue blob here and there's too much light, but you should be able to see what happens as this region expands. This is a simulation that I'm going to show you, a numerical simulation, involving dark matter that doesn't interact electromagnetically. And it's a simulation of about, I think, 6 billion particles of dark matter. This is expanding as the universe expands. This is a small region about the size of our galaxy. And what you can see is things light up. When the dark matter becomes dense enough, normal matter falls in, and you can show that the stars will form. So dark matter has begun to collapse, and stars have begun to form. And you can see eventually the dark matter on these simulations will, this Z, when it goes to 0, is today, will eventually form something that looks like our galaxy. This is a simulation, and it's only been possible in the last 15 years with supercomputers to simulate this many particles. But we now know we can actually make something look like our galaxy. And our galaxy can only have formed because the dark matter collapsed first. We would not be here if it weren't for dark matter. So we've already learned in some sense why we're here, if you want to ask that, which is because dark matter's here. We learned it by an accident, but thinking about our galaxy. But our galaxy isn't the only galaxy in the universe. Okay, here's a simulation of a whole region of the universe, about 100 million light years across. And we again can simulate this with supercomputers. And you can see very quickly, because of gravity, dark matter begins to collapse in a time. Normal matter doesn't collapse so quickly because it has pressure, because it interacts with light. And the pressure of light stops it collapsing. But dark matter can collapse quicker because it doesn't interact with light. And what we discovered, and this was only, again, since I was a graduate student, we predicted that there should be large filamentary structures. These are hundreds of millions of light years across, that galaxies should, visible galaxies should fall in the regions where dark matter is densest. And we should see a honeycomb of galaxies. That's a prediction, okay? Now, we never were able to observe that until recently. But here's a video from one of the most recent observational projects looking. This is the actual universe. We're finally able to measure the distance to galaxies. And this is a simulation. This is not a simulation. This is a measurement, I think, of about 2 million galaxies in our neighborhood. And we're going to move through it. This is the real universe. It's not a simulation. And the real universe looks just like the simulation. But if you can move faster than the speed of light, each of these things is a galaxy. And the interesting thing is, this is not just painted on. This is not just artificial. These are the exact spots where these galaxies are. This is our region of the universe. Until about 15 years ago, we could never map the universe, even in our local region. Now we know where we are, where our neighbors are. And while we'll never be able to have spacecraft that can traverse these kind of distances, we can do it in our minds, and we can do it having discovered where they are. If we could, this is what our region of the universe would look like. And the galaxies aren't randomly located. They are on filaments on large scales, giving us further confidence that this universe of dark matter is what the universe really is. And it's the first bit of real evidence that confirms something that we should all realize. That is, we are completely insignificant. That everything we see is completely insignificant in a cosmic sense. Because while the stars are here, the dominant stuff in the universe is dark matter. It's responsible for our existence. And you could get rid of us and everything we see in that beautiful night sky above that river of the Milky Way, and the universe would be essentially the same. We are just cosmic bystanders in a sea of dark matter, and it turns out dark energy, which I won't even talk about today. We are so much for a universe made for us. It's clearly, we are just lucky bystanders, and we should enjoy it. Okay, this is the universe we see. This is one of my favorite Hubble Space Telescope pictures, the Hubble Deep Field. Every dot in this image is a galaxy, except for that one. That's a star. But so, and you can, the faintest galaxies here are about 12 billion light years away from us. About 90% of the way back to the beginning of the universe. So the light from all these galaxies is interesting to think about. Whenever you look at an image like this, it should inspire kind of amazing thoughts. Because these galaxies, so this light, the faint galaxy light, left that galaxy 10 billion years ago. Our sun is 5 billion years, 4.5 billion years old. That means it left before our sun and Earth and our entire solar system formed. But more interestingly, our sun will last about 10 billion years. Most main sequence stars like our sun will last 10 billion years. That means most of the stars in this picture don't exist anymore. They're gone. They burnt out. And any civilizations that existed around those stars and had skeptics conferences, they're gone too. And we'll never know about them. And that's what's going to happen here. Everything that matters to you, everything that matters to each of us, is important to us. But the universe not only doesn't care about it, in a time, in a cosmic time that seems like a wink of the line, everything that we've ever accomplished as a species will be forgotten. Because the Earth and everything around it will go. Now, maybe we'll be smart enough to leave the Earth, we'll see. But quite likely, our sun's going to burn out, and in the long run, everything we cherish will be gone, so enjoy it while you can. Okay, going back to our galaxy. That's that picture we can see from the southern hemisphere. It's beautiful. But, well, let me go back to that, actually, that picture. So here are the stars you can see. Now, one of the big questions that humans had, eventually, once they began to allow themselves to think more about a universe in which they might not be the center, was, okay, the Earth exists. Does life exist elsewhere in the universe? It's one of the most pressing questions today. It's been a pressing question of every child has asked that question. Look up at the night sky. Are we alone in the universe? It's terrifying to think that we might be alone. For some people, it's not. It's comforting because that makes them feel like the universe was created for them. And in fact, the Catholic Church burned people regularly who suggested early on that maybe the Earth wasn't, the solar system and the sun wasn't all there was, that there were other planets. And the question is, are there other planets and could there be life? This is a question that may be answered in the lifetime of some of the people in this room. And again, I would never have thought in my lifetime that we'd be able to even get as far as we have. Because, so let's say if we want to look at a planet around a star. So this is a planet around a distant star. Well, you can see it. It's culting the star. But that's if you're close by. If you actually look at what the Earth, say, would look like if you were far away, then we can sort of move away from it and see what the actual Earth would look like if you were far away from the star. And of course, it would be totally obscured by the star. And the star, that's if you're close to the sun. But if you're far enough away from the sun, if you're on a distant planet looking around for life in our solar system, this is what you see. And so it seems impossible that you could ever actually look at planets. What is amazing is that we can. And again, I'm not an experimentalist because I wouldn't have thought we could ever do this. So here's a planet going around a star, and what happens is the planet gets bright when it's behind the star because it reflects the light, and then when it goes in front of the star, it reduces for a second the brightness of the star, and then it's bright again because it reflects the light from the star until it goes behind the star and it gets dark. Now this of course is far over scaled. This is what you'd expect to see. But this effect, it would be less than 1% in the brightness of the star. But astronomers weren't daunted, and so among other things, either they're stupid or they're good, and in this case they were good. This is the Kepler telescope, which was sent out to look at a region of the galaxy, a small region of the galaxy right here, and just stare at those stars every single day and measure the brightness of those stars every single day. Again, this could not have been done when I was a graduate student. It could not have been done when I was a junior faculty member because we needed CCDs. We needed objects that would allow us to measure and digitize the position of millions of stars and look at them every night and compare digitally, because humans could never do that themselves. And what of course the Kepler satellite has discovered, and it's a little dark here, is over 2,000 planets around nearby stars. And what you can't see is that most of the planets are inside the orbit of Mercury. Here are the set of planets. This is not all of them. This is just some set. Mercury would be out here. And the reason for that is that, well, why is that? I'm going to ask again because I want to keep people awake. Anyone got an idea?
Fast, so we can see it often enough to detect
Exactly, right? If you got Jupiter or you got a planet that's orbiting once every 20 years, in order to see that effect and replicate it enough that you can test and get rid of the noise, you have to measure it for over 100 years. We haven't been able to do that. So what you look for is planets that are going around their stars very quickly. Well, how can they do that? Because they're close by. Moreover, not just they're close by, but most stars in our galaxy are smaller than our sun. And so the planets can be closer in. And what we've discovered is, what's amazing is, not only does almost every star have a solar system around it, something that many of us thought was true 40 years ago because of physics arguments. We now know it. But there are solar systems we never thought were possible. We thought we're typical. It's always reasonable to assume you're typical. We have rocky planets inside, gas giants on the outside. What we discovered is everything can exist, stuff we thought was impossible. There are solar systems with gas giants inside. How can that be? Well, we now realize they can move. Never thought they could because of the effect of other planets. We've discovered lots of planets, and in fact, around small stars, including around the nearest star to our own, Proxima Centauri, we've discovered planets that may be in what's called the habitable zone, which means there's liquid water. Maybe. And we know when we're trying to look for life, we know we're like drunks who leave a bar and lose their keys. Where do you look? You look under the lamppost. So, why? Not because it's there. It's the only place you can see it, right? So, when we think of life in the universe, lots of different life can exist. I mean, you talk about Star Trek, and Star Trek's been good to me. So, you know, most of the actors in Star Trek most of the aliens had 2 arms and 2 legs, because most of the actors do. But we have no idea what the spectrum of life can exist in the universe. What systems? We've discovered extremophiles here on Earth that can live in regions of boiling water, acid, all sorts of regions that we never thought were possible. But we do know that life arose here on Earth because there was liquid water, organic materials, and sunlight. So we say, let's take a first pass and assume if we're looking for life elsewhere in the universe, we'll look for liquid water, organic materials, and sunlight. And all of those things exist. And so we now know that there are many, 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 many planets, including potentially around the nearest star to our own, 4 light years away, that may have liquid water, which is one of the reasons why I guess I'm excited. I'm part of a program, a very science fiction-like program, called Breakthrough Starshot, that's funded by a Russian billionaire. And me and Stephen Hawking and a few other people about 20 of us are on this planning committee to try and create a spacecraft to go to the nearest star in a human lifetime at 20% the speed of light. We do that because a spacecraft is 1 gram, because you're never going to send humans there, and forget whatever Elon Musk may think he was going to do. It's not going to happen. But we do it using a light sail. We're going to have a sail, and we're going to have lasers pointed at it, if it works, and accelerate it up in 2 minutes to 20% of the speed of light, and in therefore 20 years it'll get there. It's 10 years of R&D, 20 years to get there, and we're going to put a little camera on it and take a picture of that planet, and maybe, you know, see a water world, and maybe green, all sorts of neat things. And then it'll take 5 years for that picture to come back. 35 years, that's why I work out every day, yeah. Okay. I want to be there then. But we may not need to do that. With advanced telescopes, and there are terrestrial planet-finding telescopes, we may be able to image planets and look for things like oxygen. Free oxygen didn't exist on Earth. Life created the oxygen that's on Earth. It's very important. If the oxygen was there at the beginning, life never would have formed, because oxygen is a poison. It oxidizes. And all the organic materials on Earth would have been oxidized if oxygen had been there. It's not. So if you look at a planet, you can visualize its atmosphere and see it, then maybe if you can look for oxygen, spectral lines of oxygen, that's a good sign there may be life. So stay tuned. We may find out in this decade or the next decade about life elsewhere in the universe. And that may be, well, would that be a profound change? I don't know. But it'd be profound for me. Okay. Now, go back to our galaxy. Oh, yeah. I remember what I want to do. We're getting near the end. Oh, good. Okay, it'll be about an hour or so. He told me he wanted me to go at least an hour, so I have to. Okay, so this is our galaxy. And what you notice, of course, is the center of our galaxy, a dense region in the center of our galaxy. I want to now take you on a voyage to the center of our galaxy here. So let's do it. The fact that we can actually visualize stars near the center of our galaxy is amazing. Each time, looking at regions that have been amplified with telescopes, and when we look at the center of the galaxy, we can actually, if we measure it over 30 years, measure the motion of those stars in the center of the galaxy. And what we discovered is something remarkable. So let me look at this in a different way. Now I want to show you the years we did it. And by we, I don't mean me, okay? But watch this. This is over 1992 to about 2006. So we saw that's, and this is repeated so you can see it. Now, why do we care about the motion of those stars in the center of the galaxy? Because if we focus in, this is what we see. We see they orbit. And we can use the law of Kepler and the law of Newton and weigh whatever this star is moving around and this star. And in fact, we don't have to just do this star. We can look at all of these things. So let me just show you another video where you can we've actually labeled the stars. I think this is a video. There we go. And we just look at not just one star, but many stars, and you can see they swing by something that isn't shining. There's not a sun there in the center of that ellipse like there is for the solar system. This is a hand-drawn star, in case you wondered. The stars don't look like that. They're all orbiting around something dark. And we can measure the mass of that thing by using exactly the same principles that I told you for measuring the mass of the sun, because if it works, copy it. And what we discovered? Whatever is here has a mass of 2 million solar masses. And this region is so small that the only way you can put 2 million solar masses in a region that small is if it's a black hole. And so we've discovered, we've now actually seen the objects orbit a 2 million solar mass black hole in our galaxy. And it's amazing to me that we can actually visualize this and that astronomers can measure over decades carefully enough the motion of stars to see that there's a 2 million solar mass black hole in our center of our galaxy. It turns out we've discovered that there are black holes in the center of almost every galaxy. In fact, our galaxy is anomalous. In Andromeda, there's a black hole of 2 billion solar masses. And one of the big open questions in this kind of astronomy is the chicken and egg question. Which came first, black holes or the galaxy? Because maybe you had to have gas collapse and form a massive black hole around which other gas could collapse, or maybe stars would form and combine together and collide and collapse into black holes that would merge. This is an open question. We don't know the answer. Which came first? There are two ways we're looking for the answer. One is to build the James Webb Space Telescope, the next generation space telescope, which will be launched in 2019, because it will be able to look back to the first galaxies that ever formed and look for black holes in those galaxies to see which formed first. So it'll look at what we call first light. It will look at the first stars that turned on. We think around a time around 300 million years into the Big Bang. The first stars would have formed, and that's one of the many things the James Webb Space Telescope will do. But the other is to try and see if there are other black holes in our galaxy. And I want to sort of get near the end by telling you about, again, just thinking about our galaxy, taking you to the most amazing discoveries that we've made and some of the most amazing ideas I know. I mean, well, you'll see. You can decide if you like it. Did that just go off for a reason? Oh, there it is. So this is the LIGO Observatory. This is in Hanford, Washington, in a plain of I guess, close to eastern Washington. There's an identical one of these in Livingston, Louisiana. And this is a gravitational wave observatory. This was designed to measure something which, once again, I would have never thought we'd ever be able to measure. Einstein told us that matter curves space. And therefore, when I do this, I'm curving space, but I'm moving around, so I'm producing a disturbance in space. And you can calculate that that disturbance will ripple outward at a speed equal to the speed of light. Just like when electrons jiggle in an atom, they produce light electromagnetic waves that travel at the speed of light. General relativity tells us that when I do this, I produce a gravitational wave, a ripple in space that moves out. There are ripples in space going through all the time, but you can't see them because gravity is so weak. But right now, this room is full of gravitational waves, and it's causing the size of this room to change. When a gravitational wave comes by, the room gets a little smaller in that direction and a little bigger in that direction. Again, for some of you who drank too much last night, you're probably noticing that right now. But it's there. But you can say, well, could we ever see gravitational waves? And you say, let's look. Well, the intensity of gravitational waves gets bigger if you have more violent motion of matter. What more violent motion to matter could you have than the collision of two massive black holes if they exist in our galaxy? Two solar mass black holes. So this detector was built to try and look for that, if you come back to it instead of me. Okay. And well, all you do is if a gravitational wave comes by here, comes down, this arm, which is 4 kilometers long, and this is 4 kilometers long, this arm will get smaller and that one will get bigger with a frequency equal to the frequency of the gravitational wave. They'll oscillate. Okay, so that's all you have to do. It's easy. Okay? But the challenge is amazing because it turns out we can calculate what you'd have to do to be able to see the collision of two black holes in our galaxy or in a nearby galaxy, of two solar mass black holes, and the requirement is amazing. To measure two solar mass black holes colliding, you'd have to be able to measure a change in length of this 4 kilometer long tunnel by an amount equal to 1/1000th the size of a proton. Now you laugh, and you should, because no science fiction writer would ever dream of suggesting you could do that. But that's what these guys decided they could do. I thought they were crazy. Because if a truck hits a pothole here, it produces a bigger signal. Okay? If the wind blows, it produces a bigger signal. Now, and you also have to be able to make the measurement, which is very complicated because what you do is run lasers back and forth. But that's one of the reasons there are two of them. Because there's noise in this all the time. But there's noise in Livingston, Louisiana detector all the time. But at the speed of light, if a gravitational wave comes through here, it takes 8 milliseconds to get down to Livingston, Louisiana. So what you look is the signal in both detectors, and you look for exactly the same signal 8 milliseconds later. And in September 15th, 2015, an amazing thing happened. The detector had just come online. It had just been improved after 15 years of being developed. And Ray Weiss, who recently was one of the 3 people who won the Nobel Prize, this discovery, said, okay, we got the right sensitivity. Let's do an engineering run. We won't take data. Okay? The graduate students, being graduate students, happily didn't listen to him. They turned on the detector, and 1 hour later, they discovered the signal from two black holes colliding 1.3 billion light years away. Now think of that for a moment. That meant the signal, it was just a 0.2 of a second burst, as I'll show you in a second. That signal was traveling for 1.3 billion years. If they turned on the detector an hour later, they would have missed it. It's amazing how lucky it was. And it was a beautiful signal, and this is what it would look like if you could see it, because the black holes are so massive. This is a black hole of 36 times the mass of the sun. This is a black hole of 29 times the mass of the sun. And they bend space around them. So as they move around, if you look through them, the stars behind them get lensed. And this is what you'd see. Now this is slowed down. They're really going around each other 200 times a second. 30 times the mass of the sun, 200 times a second. It's hard to believe that can happen in nature, but they do. But watch what happens when they coalesce. You'll see ripples in space. Watch carefully. Here we go. See the space ripple? Now this is an artist's rendering. This is not what but that was the emission of gravitational waves. Now, there's 2 things I want to say that make this amazing. One is, and I need a mathematically literate person, but you're all mathematically literate. So we had a 36 solar mass black hole and a 29 solar mass black hole. Combined together, 36 and 29 combined together, they form a black hole of mass.
50-something.
What?
50-something.
No. 36 and 25. We need mathematically 29. 65. Who said 65? Who's the first person? You? Wrong. Because, in fact, they form a black hole of mass 62 times the mass of the sun. Why? Because 3 solar masses of energy were emitted in gravitational waves. Now, you should, if you didn't sigh then, let me put it in context. The sun, which is burning 100 billion hydrogen bombs every second for 10 billion years in its lifetime, will convert less than 1% of its mass into energy. In 0.2 of a second, in that instant, that collision produced 3 solar masses of energy in gravitational waves, meaning in that 0.2 of a second, that object was emitting more energy in gravitational waves than all the rest of the stars in the visible universe combined are emitting in energy. Isn't that amazing? Now, if you weren't amazed by that, try this. Sometimes stars collapse and don't form black holes. Sometimes they form objects called neutron stars. When most stars explode, what happens is they collapse, the inside of the star collapses, until finally it becomes so dense that it becomes one gigantic atomic nucleus. A neutron star. A neutron star is basically more than the mass of the Earth, a fraction of the mass of the Sun, whose size is the size of Manhattan. All of that material is compressed into an atomic nucleus, the density of an atomic nucleus, but then nuclear forces take over and it can't compress anymore. And that produces a shock wave that blows the rest of the star out, a supernova explosion. But the neutron star that's left over weighs billions of tons per each cubic centimeter of material. And many, many stars end their life as neutron stars. And what's amazing is, it turns out, for some reason that it still amazes me, even when a star explodes, sometimes the nearby star around it that's orbiting around it survives, and then it explodes. And it turns out most neutron stars are in binary systems. So neutron stars are dense and massive, not quite as dense and massive as black holes. But we figured that if the gravitational wave detector could detect colliding black holes, it might detect colliding neutron stars. And in February of this year, LIGO was operational and another detector called Virgo, and they detected the collision of two neutron stars. But what's neat is, with a black hole, there's nothing there but gravity. It's a hole in space, and the only thing that's produced is gravitational waves. But if you have a neutron star, you have stuff. So when those objects are orbiting each other and colliding, sure, they produce lots of gravitational waves, but they produce a lot of other stuff. And Virgo and LIGO were able to tell the rest of the astronomical community, hey, we just discovered a gravitational wave from two colliding neutron stars, and every telescope in the world, of every type, was turned to that region. Visible light, ultraviolet light, X-rays, gamma rays. It's the first time that 70% of the astronomers in the world all looked at the same thing because they were alerted by LIGO and Virgo. And this is sort of, again, an artist's rendering of what happened. But so here are the two neutron stars colliding. And the first thing you're going to see are gravitational waves emitted. That's what these and there's the sound of the gravitational waves. It's actually in the audio frequency. But then you produce this incredible burst of gamma rays, and then afterwards this incredible burst of X-rays, and then ultraviolet light and visible light. And we could predict, using the laws of physics, what we thought would happen. Now, what's amazing to me is we have confirmed something that should make all of you... How many people are wearing something gold right now? Some of you. Okay, good. Some of you. Excellent. And it's valuable to you. Okay? Well, where does gold come from? It's been a big mystery from the stars, but no, it doesn't. Because as some of you heard from me before when I talk about the history of stars, when stars burn, they make helium, and then carbon, and then nitrogen, oxygen, iron, oxygen, silicon, and then iron, but they stop burning when they form iron. They can't, because iron is the most tightly bound nucleus in nature. Stars can't burn fuel heavier than iron, but gold is. Where could it come from? We imagined that maybe it might come from a place where the matter was very dense and there were lots of neutrons, neutron star collisions. Maybe the gold came from there. If you could go back to the image, when we were actually able to measure over the period of the next month radioactive elements forming and decaying, producing X-rays, and observed that in that collision, 1 solar mass of gold was formed. But that means, not only were we right, but it means, think about it. It means if you're wearing gold, then the atoms in your ring or whatever you're wearing had to come from the collision of two neutron stars, the densest objects other than black holes in the universe, and then make their way to you. I mean, isn't that amazing? I mean, it really is. It's worth applause because, and it all comes from just thinking about our galaxy. So, I think I'm exhausted you. There, okay, there's the gold, of course, and we're watching the Olympics now. I actually thought of this first because it's kind of interesting that you know, I try and connect this to culture in a way. It's kind of amazing. So the Incas were destroyed because we wanted gold. Okay, gold has been a geopolitical driver throughout human history. And it amazes me so that this central aspect of our culture that's caused civilizations to be exterminated is an accident of a remnant of the most amazing esoteric collision in the universe, and how it's affected our culture. So how the way we behave is an accidental remnant of these amazing, obscure, esoteric things in the universe. Okay, that's what happens when you think about our galaxy. Just looking at the rivers in the sky, and sure, it was pretty to imagine for these primitive civilizations that the Milky Way was a river in the sky. It was a beautiful story. But like everything else, what science does that religion hasn't been able to do and never can do is take that beautiful story and make it better. And follow it wherever it takes you to discover things you never would have dreamed of. And that's the beauty of science. Thank you.
Lawrence Krauss, ladies and gentlemen. I'm sure there's no questions. So we have time for a bunch of questions. So hands up, who wants first question?
Yeah, I'll
first
take
question.
a few questions.
Right here.
If we could put a LIGO in orbit or on the moon, could we detect earthquakes instantaneously on Earth?
No. It's easier to detect earthquakes on Earth by being on Earth. But earthquakes, anything that happens on Earth would be undetectable by LIGO. But what we want to do, I don't know why I'm playing with this now. What we want to do is actually put not LIGO in space, but we want to put a gravitational wave detector that's much bigger. LIGO is 4 kilometers long. We want to put a gravitational wave detector, the first one we want to build in space, it's 4 million kilometers long. Now, how can we do that? Well, in space, you don't need a tube. You just need mirrors at either end. So if you're very careful, you can hook up mirrors at either end. And what we've discovered in a pilot mission that was just sent up is we can actually keep them at a distance where we can actually, in principle, do that. And if we do that, we may be able to detect a whole different type of gravitational waves from a whole different set of objects. And not in the next generation or the next generation, but by the 22nd century, we may be able to detect gravitational waves from the Big Bang. And then we will be observing the beginning of the universe. So stay tuned, some of you. Okay. Next question.
I heard about the shard that came through the solar system a while ago.
Oh, yeah.
Have they refined the orbit from that or anything?
Well, yeah, no, recently it was kind of the first, I think it was the first, we know it happens, but it was the first direct observation of an extra solar system visitor, not a being, but it was actually an asteroid which came zipping through the solar system and had a bigger than escape velocity from the solar system, probably produced in the explosion of a star or a solar system. And so we could actually see that its escape velocity was bigger than the sun. We can measure it over a few weeks, come zipping through. And so we now know that something we knew before, but now we know observationally, we are visited by visitors, namely asteroids, from throughout the rest of the galaxy. That could be important because, coming to the biology again, life originated on Earth about as early as the laws of physics allowed. Within 500 million years, the oldest fossils are discovered in Australia and a few other places. Now, that's really short time. Life couldn't have formed earlier because there was bombardment on the Earth by other asteroids that would have vaporized any oceans. But Jupiter ate them all, or it kicked them out. And over about 200 or 300 million years, the bombardment by asteroids went down, and the Earth became quiescent and could have oceans. And within a few hundred million years of those oceans forming, the oldest fossils formed. Now that means one of two things. Either life is just easy to form, in which case it's ubiquitous everywhere in the universe, which would be great, or perhaps life didn't form on Earth. Maybe it arrived on Earth. And Francis Crick was the first person to suggest something called panspermia, which was with the idea that maybe, because we now learn that organic molecules exist in space. The basis of amino acids are observed in our solar system and can survive potentially interplanetary and maybe interstellar voyages. So maybe complex organic materials from a deceased life form arrived on a host asteroid and polluted the Earth, allowing life to form. We don't know, but it's certainly a possibility. And so the fact that we now see these things coming in, happily it didn't hit the Earth, but some of them do, and some of them will. If we wait long enough, there'll be an extra solar system asteroid that'll hit the Earth and do great damage. So it's really an interesting object to see, because it may answer these questions, because we'll discover that a bunch of ways. One, by looking for life elsewhere in our galaxy. I'll answer one.
Question here in the back.
Okay. Mm-hmm.
Regarding the dark matter and how 90% of the known matter, or at least the unknown matter in the universe, would be not emitting any type of visible or spectra of light in any way, would it be possible that the material that is causing all that gravitational attraction be particles of which we know hardly, if at all, interact with known matter, such as neutrinos or Higgs particles?
Well, it's a very good question. The Higgs particle interacts strongly with matter and with light, so it's in a way. But Higgs particles also are not stable. They actually decay in a fraction of a second. But neutrinos are great candidates for dark matter. They were the first candidates for dark matter, because there are 10,000 billions of neutrinos going through your body every second right now coming from the sun, and you don't notice them. They're the perfect candidates for dark matter. And in 1980, I remember when I was a graduate student, a discovery was made that said, hey, these neutrinos we think have exactly the right mass to be dark matter. And it was wrong. And then we built simulations of a universe that would look like a universe dominated by neutrinos, and we discovered it didn't look like our universe. So neutrinos are the perfect candidate for dark matter, but they're not. So we look at objects that are like neutrinos, heavier versions of neutrinos, and it turns out every fundamental theory in physics right now that goes beyond what's called the standard model predicts particles that have those properties. And that's why we're actually doing a contest. We're building detectors underground. I'm happy to say many of which I proposed years and years ago, underground, to look for dark matter. But we might also create it at the Large Hadron Collider, which is also looking for physics beyond the standard model. So we don't know who will discover dark matter first, whether we'll create it in the laboratory, in a microcosm of the Big Bang, or whether we'll look at the ones that come from the Big Bang. Or maybe we're just wrong, which is also exciting. It's more exciting usually to be wrong. Just like when Vera Rubin got the wrong answer there, it was much more exciting than if she just, who the hell cared if we got the mass of the galaxy to 5 decimal places? But no, by being wrong, we discovered dark matter. So being wrong is really neat.
Here's Bob Novella from the Skeptic's Guide.
Can you give me a quick overview of the next quadrillion years? What's the latest thinking at the end of the universe?
It's not looking good. It's going to end badly. So the future is miserable on the whole. So the next quadrillion, and it's good you asked in those terms, because basically, because the universe is expanding, and I didn't talk about it in this lecture, it's expanding faster and faster and faster. All the galaxies we now see will disappear, because eventually they'll be moving away from us faster than light, which is allowed. We lie to you in high school. We don't lie, you just have to parse it more carefully. We say nothing can travel faster than light, and that's true. Nothing can travel through space faster than light. But space can do whatever the hell it wants. And space can expand faster than light, and it is. And it turns out if we wait 2 trillion years, then every galaxy we now see beyond the local cluster that's bound to us will be moving away from us faster than light and will have disappeared. And I find it very poetic, because it means in 2 trillion years, by the way, there'll still be stars, main sequence stars, there'll still be small stars, and our galaxy will still exist. It won't be spherical anymore, it'll be elliptical, because Andromeda was collided with it, and other galaxies will. But you can imagine life forms existing and evolving, we can still say that, evolving around stars in our galaxy, and producing astronomers and scientists, and they'll build telescopes, and they'll look out, and they'll see the universe we thought we lived in 100 years ago. they won't know of any other galaxies. They won't know the universe is expanding because our probes for the expansion of the universe are other galaxies. So it's really, it's not only we live at a very special time, namely the only time when we can know we live at a very special time, which is facetious because every time is special, but it also means that the longer we wait, the less we'll see. I've tried to argue to Congress that should mean we should build more telescopes now, but 2 trillion years and 2 years are very different for Congress people, and so they won't do it. But anyway, so the future is cold, dark, and empty. And eventually, beyond that, the stars in our galaxy will burn out. They'll amass together to form a huge black hole, which, if we wait longer, due to something called Hawking radiation, will evaporate into radiation, and there'll be nothing left but radiation getting ever colder in a dark, empty universe. And that's the future. So it's a good place to end.
That's a good place to end. Let's just do one more. Let's just do.
Okay,
I know. It's a good.
Such a poetic place.
It's a good place and a kind of a sad place too. So
okay,
maybe
let's ask.
Let's one more.
Question.
I'm sure this is gonna be awesome.
I'll try to make it quick. I promise. Well, I'm actually a physics major, and very quickly, I want to thank you for your amazing inspirational lectures. You've actually one of my big inspirations for being a physicist myself, cosmologist specifically.
Oh, thank you. Thank you very much.
And so right now, I'm still at a community college, and one of my hoping to transfer this semester. And my physics professor, I wouldn't call him a creationist, but he's certainly a Christian. Mm-hmm. And when he was going through the section on cosmology, specifically when we engage in the topic of fine-tuning, he started essentially trying to insinuate that this must be indicative of a divine creator. And he said that, I probably wouldn't say divine, but he certainly insinuated creator. And he said that the only reason why the multiverse theory exists is just to try to solve and get rid of this fine-tuning problem. And I was wondering, how would you respond to that?
I mean, yeah, he's responding. I wrote a book called The Universe of Nothing, and a lot of people respond to it because I talk about the fact that our current picture suggests not only the picture I've told you about our universe, but that our universe isn't unique. Quite likely there are many universes. And that may explain certain features of our universe. And the theologians say that's them just saying they can't explain the answer. Now there's 3 things I have to say about one. One is a quote that I've said often and I've seen on coffee cups now, but it's true. So lack of understanding is not evidence for God. It's evidence of lack of understanding. Okay? And so it is true we don't understand a lot of things, but what's really neat is we try to understand them. We don't just say, you'll never understand them. It's God, because that's code for not thinking. Okay? So that's the first thing. But the second thing is we've been driven to this idea of a multiverse not because it was attractive to physicists. In fact, to most of us it's kind of repulsive in many ways, because it might mean the fundamental constants of nature. Well, I grew up when I was your age, wanting to be a physicist to know why the universe was the way it was. But if it's just an accident, it's kind of depressing, right? If the fundamental constants are, and if they were different, we wouldn't be here, right? That's this anthropic principle. They are what they are because we're here to see them, not because we were created to see them. But if they'd been different, we wouldn't be around. So there may be universes where there aren't such meetings because the laws of physics don't allow such meetings. So we're not surprised that we find ourselves living in a universe in which we could live. It would be amazing to find the opposite. Okay? So that may be true, but it's not very appealing from a fundamental perspective, but we've been driven to it. So it's totally different than the notion of a creator where you start with something you want and try and make all the evidence fit, which it doesn't, but I'll make all the evidence fit. Instead, like I showed you here, we follow where the data takes us. And the data has taken us not just to the idea that there may be many universes, but as I described in that same book, all of the data suggests that our universe was created spontaneously from nothing. And if you ask, what would a universe look like that would be created spontaneously from nothing by known laws of physics and no supernatural shenanigans, it would look just like the universe we live in. Does that prove it? No, but it makes it plausible, much more plausible than the fairy tale your professor believes in. Thank you.
That's an ending. That's how you do it. Lawrence Krauss, ladies and gentlemen. Lawrence Krauss. Awesome. We go where the data takes us. I love it. I love it. Let's just finish out the day. I'd like to invite every volunteer and every speaker that's still here. Please come on up onto the stage. I know it's awkward and weird, but come on up, everybody. Every volunteer, every speaker, please. please come on up to the stage. We're going to do a big, get your phones out, take pictures of everybody. Please post this now on all of your social media. Come on up on stage, come on up on stage. We're going to do a big picture. Oh, look at this, look at this. Hashtag Logical LA. No space or anything, right? Just no dashes altogether. Get your cameras out. Look at this, look at this. Oh, that's fantastic. Yeah, less tall people in front, please, if possible. Less tall people in front, if possible. Oh, look at that. How about a round of applause for all these people, ladies and gentlemen, making Logical LA possible. Thanks to all of our volunteers. Behind the curtain, we had Mike, we had Nuno working very, very diligently, making stuff work. There's Mike over there. Thanks for making it all possible. Are we good? I think that's fantastic. Thank you, audience, for coming. Don't forget, there's still a dinner this evening. I'm doing a concert tonight as well. Tickets are still available for that if you want to go do that. We're going to have a fun little time. And here is the man himself. Here's Bruce.
Thank you all for coming. And one big hand for George, making this happen. Thanks, everybody. One last announcement. We have decided to put on the 2019 Logical. Tell your friends, tell your buddies, tell your science friends, tell your skeptic friends. We are putting it on. We have no idea where, but that's okay because we have the volunteer crew, and it's an all free, or not free, it is all free volunteer, all free for me. It's a volunteer crew, so please thank them on the way out. They spent 3 days. Not only that, but one big plug for Melissa. Are you here, Melissa? Melissa, give a round. My coordinator spent months and months and time, and her husband Tom spent time. Thank you, Melissa, so much. And I guarantee you'll get something more than just a volunteer fee next year. I'll see you all next year.